Hey guys, Max here, and in this video I'm gonna show you what I did to my Type 1 hypervisor. Um, if you are following my channel or you have maybe seen the first video, I was able to successfully boot the minimal Linux distribution on my Type 1 hypervisor, and yeah, for maybe in case you don't know what the previous video was about, so long story short. I decided to write my own type 1 hypervisor based on self-4 kernel. Yeah, it's mathematically verified. I mean, like completely verified microkernel, which provides you with the most basic functionality, but the rest is up to you. So, which is obviously also VM capable. So I just went with it because um, I didn't want to write my own kernel from scratch, bothering with all the like interrupts and all this kind of shit. With all the respect, sorry, just the interrupts is just that's the topic I hate like the most, and I'm gonna come to it a bit later. But yeah, so yeah, that's what I decided. So all right, let's take the kernel and let's build a full virtual machine manager on top of it. So again, there's no QEMU, there's no KVM, there's just nothing here. You can even like allocate memory, because a memory allocator is, I mean, like a heap allocator is very dynamic, and it can be mathematically verified, so it's not in the kernel. So I had to write my own memory allocator, physical and virtual memory allocator. We were well, which is basically a user space program, which like tells the kernel to, well, please map this memory to this regions to this memory frame, etc. Right, so that's basically, and that's the funny stuff, because that's a user space program, so it's running in a user space. We don't have a direct access to the kernel, but we can basically tell the kernel whatever we want, and the kernel just does whatever we want, right? So we have it full control. Also, a large problem I saw a bit later, which I think I was able to solve, where I had to modify the kernel a bit, is that it's since the self-for kernel is deterministic, and again, as mentioned, completely deterministic, completely math-proof, machine verifiable. It was meant to work on specific CPUs on a specific amount of cores with a specific amount of RAM. Which in my case, like how I'm gonna ship this thing to other devices if it's like fixed. So the only thing is there was a couple of patches for the kernel to bring up other CPUs and use them to schedule. But um, yeah, this was one of the rather harder challenges. But so first things first, I'm gonna show you what we currently have. Let's go with a start script, and yeah, as you can see, it is booting here in the serial console, and it takes a bit more of time because, yeah, first of all, it brings up the CPUs, all the cores, and it detects all the memory over whatever memory we have. And that's the interesting thing. I make this thing, so this thing is able to work on the larger amounts of memory. And this is why it takes a bit longer on the boot up, because it has to initialize multiple page levels. Oh, and here we go, as you can see, a Linux is booting, which is not, obviously, this is not a real Linux. I mean, it is a real Linux, but it is fully virtualized. As you can see, let's take a look at the console, because here, this is the virtual, this is the box. I believe there's some basic frame device which is just wanted to pass in to test how it works, how device pass-through works. And as you can see, actually, all the device pass-through work, but the real log, both kernel and Linux, will also see here. So as you can see, um, the loader brings up the cores, so it's not even the kernel itself. It's just it's the loader which brings up the cores. I did some debugging here. Physical cores, the certain, like, many regions are mapped just one to one to the cache RAM to the physical RAM. That was done for the sake of the device pass-through, since we are not every device has IOMMU, especially Raspberry Pi, like systems on chip, and I want to keep this hypervisor like as modular as possible. And even again, it's gonna be more of a building blocks for your own hypervisors. I'm gonna come to it a bit later how it exactly it works and what to do next. I mean how far I currently am. So the VMM scans all the hardware the system got, and takes a certain device like PCIe device, etc., and just directly maps them one-to-one to the DOM0, which is basically very similar to how Sense hypervisor work. Alright, so this is kind of similar. So basically all the hardware, or nearly all the hardware peripherals, are handed to the Linux VM, so we don't have to bother with drivers, I mean file systems, networking, whatever. We don't want to bother with it in the cell core or in the hypervisor, because imagine like writing drivers manually for all the hardware to support it. It's just gonna be a nightmare. Right, so we're just and since we do not have actually I'm immune, that we don't have actually any maybe like we don't have this these groups and so on, just we don't have it. And that's the mental model. If you're using the glue virtual, this is why what I call this hypervisor. It's just a project, but whatever. If you're using it, you gotta, at least for now, you gotta know what you're doing, right? And there isn't actually any device pass-through via the. There isn't actually any device pass-through to the VMs other than to the dumps to the base to the core main virtual machine. So other VMs are totally isolated, don't have any physical device access. So that explains why we just can simply map the regions. And there are ways to just map the other physical regions to other VMs. It's not going to be a problem. So we are fully ignoring the IOMMU groups here. The good thing is we can run it on basically every system on chip and every Raspberry Pi. We can just forward a certain amount of pins or GPIO or whatever ports. We just can't map one. We can just map it one-to-one, because to this or that VM or whatever, because we just feel like it, right? In this case, for example, the UART, the serial console, is used both by the host and by the guest. And it's not a problem actually. Alright, it's not that sufficient of a device, but you generally get the idea. And again, the cool thing is we decide whatever gets mapped to whatever, and yeah. The bad thing is it's pretty bad for the security on high load enterprise, high security servers. There we have to find a way to enforce the IOMMU groups, which are dependent on chipset basically, right? And yeah, so but it's for later. Now it works, and it works pretty fine. So one of the most important things I actually added, which made it all this whole thing possible. As you can see, again, we have a lot of cores here. Oh yeah, as you can see, devices are being scanned. A new device tree binary is being built to start that, to then be passed to the dynamic, obviously, to be passed to the to the VM, so the guest Linux sees them and can like use interact with them. It's very similar to the ACPI tables in the x86, and actually from what I know, the RM has the ACPI tables as well, but I just went with the DTB because they felt like being easier, I guess. And the rest good. From what I know, they're just another like thing, another way to describe basically the same thing. So yeah. So yeah, as you can see, some device frames are being mapped, which are in our case, these are the so we have detected the physical devices and we're mapping them one to one. All right. Uh, memory map.io. All right, we have mapped everything. Awesome. We're initializing the virtual CPUs here, and we're loading the kernel. We're built. Oh yeah, we have to initialize the virtual CPUs. There, also put them into the DTB device tree binary, because again the CPU is a device as well. All right, and we just there we have some. All right, whatever. Yeah, it's just a bit of garbage. I mean, yeah, I think it's conflict. Whatever. It doesn't like disturb anything in the end. So yeah, we just set the we just run the first CPU, do the vim enter, see well the guest is alive. Awesome. It means the code has been loaded and something's happening. All right, and yeah, we are initiating basically, and we're setting all the initiating basically all the virtual CPU cores, and they're just on standby. So then it boots as it should, and as you see, GIC version 3, which is again one of the hardest things I had to deal with. Oops, which is the global interrupt controller. Gig virtual global interrupt controller. Here we are. All right, and yeah, there are a lot of things to emulate, but it's, I mean, I believe there's even a gig v3, gig 3 extended, which has the memory triggered interrupts, and there's even gig v4 with some very sufficient nested virtualization, God knows what. Um, which isn't even supported by the which is so new that it's not even properly supported by the modern RH64 RM64 operating system. So I just had to Google like what is the most popular, real fastest, the best virtual global interrupt controller for the IRM, and it was the gig versus gig version 3. So that's what I did. And yeah, because RM is still kind of still a bit messy, although it's getting better and better every time, but still. So yeah, so it's being initialized, no problem. Here you can see bring up secondary CPUs, so they're actually initialized over the gig, and yeah, obviously the secondary CPUs are initialized over the interrupts controller. So brought up one node, 12 CPUs, everything's all right. Yes, so next thing I added is the power controller, which is the yeah, this is just the power interface. And as you can see, actually, I came from the Java world and from the AOP object-oriented programming world, all right, and I just love the object-oriented programming as it is, because it makes the code much easier to read, in my opinion, at least. I mean, functional guys from Haskell may disagree with me, all right, but it's I guess it's personal. It's everyone's flavor. It's up to the programmer. So yeah, but what I did is I created a common interface. As you can see, implement virtual device, which is a common interface to yeah, to React, which has to be well implemented. And here we just extend the implement the interface, or in this case trade, all right, for our controller, for reads, for writes, for what happens on read, what happens on write, what happens on power button press, right, and on what happens on the nodes, which is in this function is used to generate the device tree binary, and it's just generated here, and everything's just packed. So I can show you now what it looks like in the main file. Yes. Yep, here we go. Yeah, here it loads. Here it gets all the physical devices, gets them enumerated. Then, as you can see, any device that's virtual, we add some virtual device, new vtimer and new PL1. We just create them as objects because they are basically object, and we just push them into into an array. Then we go through all our physical devices after we've cleaned them, in our case like PCI devices, network cards, etc. And we also push them. So because it's also a device. Yeah, there's a physical device, it's handled differently. But again, we have all this common interface building blocks where everyone can build his own hypervisor for whatever he or she wants. And yeah, the rest is pretty obvious. It's the image, the kernel image loaded at the memory. As you can see again, VM. First we're creating the VM here, like mutable VM new, amount of virtual CPUs, then the memory region we've just defined, and the devices. So 3 parameters. Very straightforward, very easy. Right, and we just write it. What to write at this address, write this, and that's it. So it's very easy to manage. And yes, on VM state change, we even have this callback if the VM is being turned off. So let's just go with it. First, let's check. Oops. CPU info. As you can see, bug on MIPS, but we got everything we needed. And as you can see, we got all the total memory. So we can just write power off sector, and as you can see, it just stops. And here, main on VM state change disabled, so this event handler just fired. Because let's say we want to trigger an alarm. Let's say we want to restore it. Let's say we want to notify something. Whatever we might be wanting to do, the VM was terminated and the state is changed. Obviously, there are functions to pause the VM, basically take off the execution scanner, but it's just too long to show now. So yeah, and here again, we're just consuming all the interrupts and forwarding it to the VM. So this is also pretty straightforward now. Yeah, so this is basically it. And yeah, in case you like it, like, comment, subscribe. If you want to see more, because again, I haven't seen actually any, or I haven't seen a lot of I haven't seen many videos about like real virtualization. I think I have barely seen any about the virtualization. There are barely any. So that's why I'm doing it. And again, in case you're interested, you're like welcome to ask questions. I'm a student myself, so please don't expect them to be sort of very professional. But I'm gonna try my best. Like with this hypervisor, I am trying my best. So again, thanks for watching and see you next time.